Okay, so let us look at the Gauss elimination process a little more formally. Um, Let us assume that we have a system which is already upper triangular. If it is already upper triangular, the system size is n, then you can write it in this way. The first row, the first equation is full, starts with a11, ends with a1n. The second equation starts with a22 because it's upper triangular, this is 0. A21 is 0, and then you have n minus 1 terms, n minus 2 terms, and finally you have only one term in the nth equation. And this is a upper triangular matrix written in extended notation. Now obviously what we do is we start the back substitution immediately, and from here xn is simply bn by ann, and then at any stage, let's say at stage j, where your equation starts with ajj xj plus a j plus 1 x j plus 1 and goes all the way up to xjn xn equal to bj. This is the jth equation. And here, when you come to this equation going from the bottom, then all these things are known, so you can take them to the other side. So you will have ajjxj is equal to bj minus summation of ajk xk with k going from j plus 1 to n. So this is how you will get ajjxj, and then dividing by ajj you will get xj. So this is the back substitution process for the jth step, and doing this you will go from j equal to n all the way up to j equal to 1, and you will get the entire solution. Now if you look at it, you can figure out how many operations are needed here. Obviously only one division is needed. Remember, in the computer, multiplication and division takes significantly more time than addition and subtraction. So division actually takes a little more time than multiplication. So if we can compare, if we can count the number of multiplications and divisions, we more or less get a measure of the time that an operation takes. So here you have n minus j operations, n minus j multiplications. You have one division, and so n minus j multiplications and one divisions for the jth step. So if you add it up, n will become n square for the n steps that you go through. J is equal to n for the first step, n minus 1 for the second, or goes all the way up to 1. So when you add the operations up, it will be a series which starts with n, then n minus 1 and goes all the way up to 1. So when you sum this up, it will be 1 to n summation, which is n into n minus 1 by 2. And then you have one division per step. There are n steps, so there are total n divisions. So in the n steps that you have to do, this will give rise to n square, this will give rise to n into n minus 1, and this one division will give rise to n. I have said that division takes a little bit more time than multiplication, but we are neglecting that fact here. We are assuming that all these are proportional to the times that it's going to take, and if you do the algebra, you get n square by 2 plus 3n by 2. So these are the number of operations that the already upper triangular matrix has for the back substitution process. In addition, if you want to be more accurate, then you have n minus j minus 1 additions. So here you are adding these terms, so you have n minus j minus 1 additions here, and then you have one subtraction here, and if you add that, this again will lead to n square for n steps. This will lead to n into n minus 1 by 2. This will lead to n. This will lead to n. Add them up, you have these many number of additions and subtraction operations that you need to do. As I said, these take much less time than this, but the basic long and short of it is that if you start with a upper triangular matrix, the back substitution process takes a number of operations of the order of n square, which means that you have a 1000 into 1000 matrix. You will have 10 to the power 9 10 to the power 9 operations. If you have a 1000-degree of freedom system, then you will have 10 to the power 9 operations in order to arrive at a solution. So this is the number of steps taken by the back substitution process. Now we start with this original problem, and we are looking at the number of operations that are necessary to get to this upper triangular system. In the process, we will also look at whether the upper triangular system is actually equivalent to the original system. Now, we do the same operations like we saw in the example before. We do the same operations on A as well as on B. So we most often we combine them into an augmented matrix, which has now n rows and n plus 1 columns. The plus 1 column because of the B. So we have to start with the original system. Let us store the original system in A0. A0 is the original A matrix and B0 is the original B matrix. And I have A11, A21 to AN1 here, and A12, A22, A1n. So this is my system, and now I'll have to eliminate the first row from here. To do that, the first thing I need to see is whether A11 is equal to 0. If A11 is equal to 0, remember, for the rth row, I will have to multiply it by AR1 by A11, and I cannot do that if A11 is 0. So if A11 happens to be 0, I scan through this row of this matrix A0 and I find a row where AR1 is not equal to 0. So find a row where AR1 is not equal to 0, and then I swap these two rows, which is called a permutation of rows 1 and R. When I do this, I get a new augmented matrix. I do that for B0 as well. And I get a new augmented matrix after the permutation, which is A0 tilde and B0 tilde. So now, after the permutation, these quantities have become tildes. And this can now be used to eliminate all this. So I will have to calculate a quantity Q, which I can call QR1, which is AR1 tilde by A11 tilde, and then multiply this row by this factor, subtract it from all of these, and then I'll get zeros everywhere. So this is similar to the problem, exactly similar to the problem the small problem that we did at the beginning of this lecture, except that we have done an additional permutation step because we encountered a 0 along the diagonal. So this is what we will do. We will find a factor Qj1, which is Aj1 tilde by A11 tilde, 0 being the original, and then we will subtract from every Aj. We will get after the first elimination. That's what this one indicates. We will multiply the row above with Qj1, subtract it from the row below, and we will do the same thing to get B1. We will take the value of Bj0 and subtract it from the rows below and the result of this operation after permutation and a sequence of elimination is a1 b1, that's after the first elimination, and that has zeros everywhere here, and new values in this part of the submatrix. This part of the submatrix, you have new values. These values remain unchanged because now u1 has been eliminated. Now this permutation operation as well as this operation of multiplying by a factor and subtracting it from rows below, both of them can be modeled, can be expressed as matrix operations. It's easy to see. So if you define a permutation matrix, this is my permutation matrix P1, where you are going to swap rows 1 and R. This permutation matrix is ones along the diagonal, ones all along the diagonal, except at 1 1 and RR where it has 0, and then it has in AR1 it has 1, and A1R it also has 1. And you can easily see that this matrix multiplying another n cross n matrix will swap rows. Let's see how that works. So let's take a small example. Suppose I want to swap rows 1 and 3 in a 3 cross 3 system. So I have ones everywhere. I am going to swap 1 and 3. So I'm going to set this 0, this 0. This will be 1, 1, 3 will be 1, 3, 1 will be 1. And this multiplies a 3 cross 3 matrix. Let's say A11, A12, A13, A21, A31, A32, this is 22, 23, 23, 33. So multiply this with this. So this row into this. So the result of this multiplication will give you A31. This into this will give you A23. This into this will give you A33. Then this into this will give you this row. So these are zeros. So this row into the first one will give you A21, A22, A23. So the row 2 remains where it is, and then here this into this will give you A11, this into this will give you A12, this into this will give you A13. So you see that this was the original thing. This was the first row. This has become the third row. This is the third row. This has become the first row. So this matrix did the trick of swapping rows 1 and 3. So if I have a permutation matrix of this sort, I can actually model the transition from the original system A augmented B to the permuted system A tilde augmented with B tilde, and that can be written as A tilde B tilde is P1 times A augmented B, where P1 is this matrix. Similarly, when you do this elimination step, here, you can express that in terms of a matrix which is called a Frobenius matrix, G1, and G1 has a form like this. So this G1 has ones along the diagonal, and you are trying to eliminate the first column, the first variable. So you have these quantities. So minus q. So q21 is a21 divided by a11. Qn1 is an1 divided by a11, and these are along the first column, and along the diagonals you have 1. Again, it's easy to see that this will lead to elimination step, So let us write this down. So this is, let's say again, for a 3 cross 3 system, this is going to be 1 1 1, and this is going to be minus of a 2 1 by a 1 1. This is going to be minus of a 3 1 by a 1 1. This is 0 0 0 0, and this multiplies a 1 1 a 1 2 a 1 3 a 2 1 a 2 2 a 2 3 a 3 1 a 3 2 a 3 3. So this is what it multiplies. So the first multiplication will give you a 1 1. So multiply this with this, then a 1 2, then a 1 3. The second one will give you uh, this one will multiply with a 1 1, so it will give you minus a 2 1, and this one will multiply with a 2 1, so this will give you plus a 2 1, and then you have a 0 that gives you nothing. This multiplied with this will give you a 2 2 into a 2 2 minus a 2 1 by a 1 1 into a 1 2, and this will give you a 2 3 minus a 2 1 by a 1 1 into a 1 2. These will lead to some numbers, non-zero numbers, but this will lead to 0. This will lead to 0. Similarly, when you do this into this will lead to 0. Here you will have some number, here you will have some number, and that kind of shows that if you want to represent the transition from the permuted matrix A naught B naught to A1 B1, you can visualize that as a multiplication with a Frobenius matrix, which has this form. The Frobenius matrix and the permutation matrix both have determinants of 1, and the inverse of the Frobenius matrix is equal to itself. So the inverse is the inverse of the permutation matrix itself, and the inverse of the Frobenius matrix is just itself with these minus signs gone. So it's a plus sign here. So now it's easy to see why Ax equal to b has the same solution of A1 x equal to b1, because they are the same systems actually. So A1 x b1 is actually A multiplied by a permutation multiplied by a Frobenius matrix. So permutation followed by elimination gives you A1 from A. Similarly, permutation followed by elimination gives you B1 from B. And this is equal to your A1, and this is equal to your B1. So this is basically the same system as A1x equal to B1. So if you take this system multiplied by G1 P1 by both sides, you get this, but that is the same as A1x equal to B1, which clearly shows that this system and this system are actually the same and they have the same solution. Okay, so having proved that the permuted and eliminated solution at one step is equivalent to the original system, let us see what is the effect of uh, n such steps of permutation and elimination. So if you do that, if you do n steps, so you go from AB, which is the original system, to A1 B1 to n minus 1 Bn minus 1, you end up with the augmented matrix RC, where R is upper triangular. Okay, and then R is obtained from AB by a set of permutations and Frobenius matrices, permutation and elimination G1 P1. This is the first one, up to Gn minus 1 Pn minus 1, where Pi is a permutation matrix which has once all over except in rows 0 and r. It has, except in diagonal elements ii and rr, it has zeros, and then ir is 1, ri is 1. So this is the permutation matrix that swaps rows I and r at any stage, at the ith stage of this process. At the ith stage of this process, similarly, the Frobenius matrix, this gi is once all over the diagonal, and below the ith diagonal, ii term, you have minus qi plus 1 comma I, which is qi plus 1 comma I is equal to a I plus 1 comma I divided by aii. So this is the q, and negative of those are present here. So the elimination process can be thought of as a set of uh, successive multiplications with a permutation and a elimination matrix or a Frobenius matrix. Now, often in many codes, we do the pivoting step, the permutation step between r and let's say 1. Even if a11 is not 0, we most of the time just take a r1 to be the largest element among in the first column and swap it with the first. If the first one is the largest element, we leave it at such. If a11 is the largest in that column, we leave it as such. If not, we swap it with a11 and look for the maximum and then swap it with a11. Now, it is possible to do what we are doing is called column pivoting. We are permitting rows. It is also possible to do total pivoting and swap rows as well as columns, but it's an expensive process and it's rarely used. Now we are in a position to calculate the number of steps, number of operations, especially multiplications and divisions necessary in the Gauss elimination process. Earlier we had seen that the number of steps necessary for a backward substitution is of the order of n square. Here we see per every step we have a set of divisions. In fact, we have n minus k divisions, and then we have multiplications which are so we have division here and division here, and then these are multiplied. So if you count, we will have n minus k into n minus k plus 1 multiplications at every stage, and then if we count over the n number of steps, we can see that the order of operations needed is nq. So by far the elimination process is the more expensive process. If you have a 1000 cross 1000, that means 10 to the power 3 sized system, n is 10 to the power 3, then you have 10 to the power 3 into 10 to the power 3 into 10 to the power 3 times 10 to the power 9 sets of operations to do the elimination. Then you have 10 to the power 3 into 10 to the power 3 number of operations for the back substitution process. So that's the total number of operations you will need in order to get a solution to a Gauss elimination problem. It can be, it goes up very fast with the number of the size of your system. So huge systems will find it difficult and time consuming to be solved with Gauss elimination. Let us look at this pivoting idea through a small problem. As I said, that the pivoting is done irrespective of whether a diagonal element is 0 or not, whether we encounter a 0 diagonal or not. Pivoting is done swapping the largest quantity in a particular row below the diagonal with the diagonal itself. So let us start with this small system and try to find a solution. So here, if we look at the first column, 3 is the largest. So this becomes the pivot, and then we multiply this by 2 by 3 first, subtract from here, and then we multiply this again by 1 by 3 and subtract from here. Okay. When we do the subtraction, this becomes 0, this becomes 0, but instead of storing zeros, we generally store the 2 by 3, which is the factor that we had multiplied to eliminate the second row, the first row from the second row, and 1 by 3, which is the factor that we used for the third row. So these factors are stored below, and as a result, these numbers also get changed because this has been multiplied by 2/3 and subtracted from here, we get 1/3. This has been multiplied by 1/3, subtracted from here, and we get 2/3, and so on. Now, the B vector has been changed as well. Now, we have to eliminate this. Now we see that 2/3 is the larger of the two. 1/3 is smaller than 2/3, so we are going to swap rows 2 and 3. That means multiply by a suitable permutation matrix. We will swap these, and when you swap this, you have to swap all the 4 entries here, and when you swap this, this is what you get. You swap these 2 rows. This now becomes the pivot. Now you multiply this by 1/3 by 2/3 and subtract from here. So when you do that, this is what you will get, and 1/3 by 2/3 is 1/2. 1/2 is what is stored here. It actually is 0. So these are actually zeros, but we have stored these factors that are used. We have stored those factors for future use at these locations. And now you have, because this is a 3x3 matrix, you need 2 elimination steps, and after 2 elimination steps you have an upper triangular system. So the first solution is 4 divided by -1/2, that is 8. X3 is 8, x2 is -7, and x1 is 19. So this example shows how the pivoting is done, how the largest element in a column is chosen out, swapped with the diagonal, and then the elimination process is calculated. Remember, the permutation process, after you have identified a pivot, the permutation process is a multiplication by a permutation matrix. The elimination process is a multiplication by a Frobenius matrix. And in this case, because it's a 3x3 system, you had 2 permutation matrices and 2 Frobenius matrices. Now, you might ask why this pivoting is necessary even when we are sure that we are not going to encounter zeros along the diagonal in our systems. It is necessary because of numerical reasons, because computers have finite precision, and there are situations when your stiffness matrix consists of very large numbers along the diagonal along with very small numbers. So here this is a very small stiffness and this is a very large stiffness compared to this. So in comparison they are very large, and the actual solution of this, if I take this to be almost equal to 0 compared to this has a solution, and the actual solution is actually x1 equal to 1 and x2 equal to 1 as well. Not exactly, this is approximately. If I take this to be 0, this is the solution, but in reality the solution, exact solution, is this and this. This is the solution of the system. And now let's do this without pivoting. That means when I eliminate this, I don't swap these 2 rows. I don't swap these 2 rows, which I should. And when I do the elimination without doing this permutation, then this is the elimination step I get. Only one elimination is needed because this is 2x2, and it leads to a wrong answer, x1 equal to 0, x2 equal to 1. Okay, so this wrong answer is uh, caused by the fact that I have not performed the pivoting step in a system where there is a huge disparity in the magnitude of the diagonal elements. If I do pivoting on the other hand, I get to the right solution. So when I do pivoting, I first swap these two. So this goes up and 10 to the power minus 4 comes down. I get a solution which is close to the real solution, x1 equal to x2 equal to 1. So pivoting is necessary and should be done as a matter of course, because you might have very large differences in the size of your diagonal elements in a stiffness matrix, and that coupled with this finite precision arithmetic that computers have may sometimes give you erroneous answers. So it is better to do pivoting. Sometimes the problem cannot be solved with pivoting either. For example, you have suppose you take the last system and you multiply this by a large number. Say you multiply it by 2 into 10 to the power 4. You multiply it by 2 into 10 to the power 4, in which case you get 2. So 2 into 10 to the power 4 minus 10 to the power 4 it gives 2, and you get 20,000 here. The second, the second row is not multiplied by anything. So the first equation I have multiplied by 20,000 on both sides. Now, even if you do pivoting here, you get an incorrect solution. So sometimes it is necessary to do something called a scaling of the matrix in order to get a stabilized solution. It is also possible to solve this problem by total pivoting, where you pivot rows as well as columns, but as I said, that's kind of cumbersome and it's very rarely done. One way would be to multiply the two matrices by a conditional, or perform what is known as an equilibration step, where D is a diagonal matrix and its elements are sum of Aij inverse. So you can construct this diagonal matrix, multiply it here, and then you will see that this system, this stabilized system, will give you the right answer, which is x1 equal to 1, x2 equal to 1. You will not get that even by pivoting. So there may be situations where even pivoting will not give you the correct answer, will not converge to the correct answer, but most of the time, pivoting is highly recommended because it stabilizes the solution.